Hey guys, we are going to go through LT2 homeostasis notes. So as the video progresses, it will follow the path of the guided note sheet that you should either have printed or made a copy of in Google Drive and are following along typing information if you chose that route. All right, here we go. We start with the concept of homeostasis, which you all have read an article about. We've had a little bit of discussion about. The word homeo means same, and stasis indicates a stable or unchanging thing. And so when we put these together, we get the idea that homeostasis is really about maintaining a stable internal environment. And so a good definition of homeostasis is the ability to regulate a constant internal environment when your external environment is changing all the time. And a great example of that was discussed in your article when temperatures fluctuate, right? When it's really, really hot in the summer or really cold, or you get cold or you get extremely hot, your internal environment, your body temperature cannot fluctuate outside of a pretty narrow range of values. And so the ability to kind of maintain stability when the outside world is hot or cold or constantly changing is critical. And so homeostasis is very much essential to life. A couple of examples of systems that must be regulated to keep us alive, systems where homeostasis is really critical. Blood sugar. We'll talk about blood sugar and the role of insulin in particular in our body must be regulated every single day. After every meal we eat, after every activity that we do, we are fluctuating blood sugar. And so that must be regulated. Temperature, again, body temperature in particular must be regulated. Water balance or retention. We learned in LT1 that the renal system or the urinary system is really responsible for regulating water in our bodies, and that greatly impacts things like blood pressure. And so we must regulate water for lots of reasons, blood pressure being one of them. And there we see blood pressure as well as something that must be regulated. And the last thing that I gave you, again, this is just a few examples of systems or processes that must be regulated to maintain life. Not all of them, by all means, but the exchange of oxygen and carbon dioxide. So this is primarily respiratory system related. But again, is something that is critical that must be regulated. If you accumulate too much CO2 in your blood, it actually becomes acidic, and that is not good. So homeostasis is very much critical to life. It's all about maintaining balance, which is why we get this little diagram right here and kind of the Goldilocks idea of not too hot, not too cold, but just right. Maintaining homeostasis requires a process. And so now we get to talk about feedback loops. Before we take notes on feedback loops, I want to show you this video. So all you have to do is watch the video as it plays on my screen.
Your body is a temple. To be healthy, the body has to keep a huge number of things in perfect balance. Welcome to the world of homeostasis, which is all about staying the same, so as worlds go, it's quite predictable, ideally. Okay, so what needs to be balanced? Let's have some specifics. The key things are water content, iron content, body temperature, and blood glucose concentration. Later, we'll look at what can happen when the body's regulatory functions go wrong, and what to do to put things right. But first, let's look at getting rid of waste. Unlike your bedroom or my house, the body cannot tolerate a buildup of waste. The concentration of waste products could affect chemical reactions and damage cells. So what things do we need to remove? Well, carbon dioxide for one. It's a waste product of respiration. That's the chemical reaction in cells that releases energy. Most carbon dioxide is carried to the lungs, dissolved in the blood, and leaves the body when we breathe out. Water is another thing we need to control. Water gets into your body through food and drink. Aerobic respiration in cells produces water too. Too much or too little water in our body cells will damage them. Although I think this fella's broken anyway. We all know what happens when we drink a lot. We dash off to the toilet. But the way to say this in the exam is, the kidneys respond to higher levels of water in the blood plasma by producing a larger volume of urine, which is also more dilute. Yes, the kidneys. Very important organs, those. What do? They filter out small molecules from the blood, water, salts, glucose, and urea. They take everything out, but then they put some of it back. They put back all the glucose, and they reabsorb as much water and salt as is needed. That leaves urea, some water and some salt as waste, which is now called urine. Not because we don't like it, that's just its name. Urine is stored temporarily in the bladder, ready to make you panic when you're stuck on the bus. Dilute urine means the kidneys have got rid of a lot of excess water. Dark concentrated urine means the water level in the blood plasma is low, so that the kidneys have not filtered much of it out. Urine concentration changes depending on external temperature, exercise levels, and the intake of fluids and salt. So now you know how to achieve exciting variations in urine colour. You also lose water when you breathe out and in your feces. But there is another mechanism for removing water from the body. That most elegant of body functions. It is, of course, sweating. That's why we need to drink more on a hot day. Sweating has another function, cooling us down. The thermoregulatory centre in the brain controls our body temperature. This centre can detect the temperature of blood flowing through the brain and also receives impulses from temperature receptors in the skin, which help it keep body temperature at around a constant 37 degrees Celsius. Pretty impressive. But why bother? Temperature extremes are very dangerous. Really high temperatures can cause heat stroke and dehydration, and if untreated, even death. At other extreme, very cold temperatures can cause hypothermia, which can also lead to death if not treated. It's just death everywhere you look, death! When your body gets very cold, it's your hands and feet that feel it first. That's because the body works to maintain its core temperature. Ooh, I better change the subject, I'm freezing. The body's cells need a constant supply of energy. This comes from glucose carried around the body dissolved in blood plasma. Blood glucose concentration is very important, and it must be kept within narrow limits, not too high, not too low, round about there. Pancreas monitors and controls glucose levels. The pancreas produces a hormone called insulin. Insulin causes glucose to move from the blood into the cells. When blood glucose is too high, more insulin is released. This means more glucose moves into cells, reducing the blood glucose level. When blood glucose is too low, less insulin is released. Less glucose moves into the cells, more stays in the blood. This raises the blood glucose level. Simple but effective, unless you're diabetic. People who suffer from diabetes cannot control their blood glucose level. This is a very dangerous situation and can be fatal. Diabetes comes in two variations, called surprisingly type 1 and type 2. In type 1, the body does not produce enough insulin. Diabetics must pay careful attention to the diet and must regularly inject themselves with insulin. Type 2 is often the result of a poor diet and obesity. It is usually controlled by diet and exercise, which is also how you avoid it in the first place. The irony. So, to recap, water balance, body temperature, salt and glucose levels are all critical to life. Homeostasis means controlling these to maintain a constant internal environment. Your body is a temple.
Oh, no, not again. Okay. So you saw many different actual examples of pretty in-depth feedback loops that are helping to regulate homeostasis. So as we enter the next section of our notes and we talk about feedback loops, Really, we're talking about systems or a process that is the primary way of regulating homeostasis in our bodies. There are two different kinds of feedback loops, and we will see both. But before we talk about those two different feedback loops, let's talk about what all loops have in common. It's best and easy to find the commonalities and then understand the differences after. So, all feedback loops require a stimulus, and a stimulus is just something that will initiate the loop, that will get the loop going. So, this diagram up here you saw in your article, here is our stimulus. And real life example, the stimulus is increasing body temperature. So, a body temperature that exceeds 37 degrees Celsius, which is that 98.6 degrees Fahrenheit if we converted it. So you have to have a stimulus in a loop. Doesn't matter what kind of loop, you got to have something that engages the loop, that gets it going. And then, of course, you have to have something that will detect that stimulus. This is called a receptor. And so if we follow the generic path, here's our stimulus. It is detected by a sensor or a receptor. Body temperature is detected by a sensor or a receptor that exists within the brain. So usually this is a sensory neuron that is out in the body. The specific temperature, blood temperature, go away. The specific not blood temperature, body temperature is detectable by specific cells in the brain, but most of the time they're sensory neurons that are out in your body. And so these receptors detect the stimulus. Sensory neurons in the body are called afferent neurons. And so this word afferent with an A, the receptor or sensory detection component is an afferent pathway. All loops then funnel that sensory information to a control center. And the control center is located within your central nervous system, or your CNS. And that is either the brain or the spinal cord. So the information from the sensory neuron must be directed to a control center. So here, the sensory neurons are actually in the brain, so it doesn't have to travel very far to then still be within the control center. A more generalized example, you would have sensory neurons out in the body detecting a stimulus that then really do have to funnel information back to your spinal cord, which then sends it up to your brain. So all loops must have a stimulus. That stimulus must be detected by a receptor or a sensory neuron. That information is sent to a control center so that you can respond. And so the last part that all loops have is a response, which is called an effector. And this is usually generated by way of a motor neuron that will go land on a muscle and cause that muscle to contract, which then produces a response. Now, when I say muscle, you probably think of skeletal muscles all over your body, and that's an example, but there are also cardiac muscles controlling our heart, and there are smooth muscles controlling pretty much all of our internal organ systems, respiratory system, digestive system, endocrine system. And so contracting or relaxing those muscles will squeeze a gland or cause part of your digestive system to contract and push food further down. So a stimulus, up here in this diagram again, a stimulus is detected by a receptor, usually a sensory neuron that feeds to a control center that generates a response, which is usually the effector pathway with an E out to a motor neuron. A response is generated, and that response then feeds back on the stimulus. So, depending on what that feedback looks like, if it is going to promote the stimulus to run the path again, then it's one type of feedback loop. If it's going to feed back on the stimulus to stop it and shut down the path, then it is a different kind of feedback loop. Okay, so over here, real life example, body temperature peaks, a region in your brain picks that up, it's interpreted, and a response is generated. Muscles surrounding your sweat glands contract, push out sweat, you sweat, and that cools you down, which feeds back on the temperature. And instead of increasing temp, now it lowers your temperature back down and you cool off, and the pathway can kind of shut down. So all loops have these four components. Now, depending again, like I said, depending on what the feedback is on the stimulus, we could talk negative versus positive loops. So negative loops are the most common of the two loops. This is when the stimulus is detected and the central nervous system will work to change, alter, or correct that stimulus. So the feedback on the stimulus itself usually works to eliminate or stop that stimulus. And so an example is what we just saw as temperature. Here you have in words what I just spoke a second ago. When your temperature increases, a region in your brain called your hypothalamus detects that, processes it, and sweating is our response to then cool our body back down. If you were to graph a negative feedback loop, so this is another thing that we would have to be able to recognize feedback loops based on a graph. If you graphed it, it would look something like this. So you're going to see a constant fluctuation. So this is blood pressure, but it could have been temperature as well. You see an increase, and that feedback loop kicks in to cause some kind of response that brings us back down to normal. So we might see an increase and a return to normal, followed by a decrease and a return to normal. So either part of this graph, increase and decrease, or decrease and then come back up to normal, could be recognized as a part of an overall feedback loop. So again, remember, you kind of start at a normal value, you move away from that normal value, either going up in body temperature or going down, and a system kicks in within your body, kicks in to return that value back to quote normal. Positive loops work a little bit differently. They're a little more rare. We see a couple examples of them, really common examples of them in the female reproductive system with nursing, the production and letdown of milk for nursing, and then also what you saw in your article, which is contractions for labor. So a positive loop, the feedback on the stimulus will work to increase that stimulus or to perpetuate the stimulus. So a great example of that we see in this picture are contractions and labor. And so here is in words what you see in that picture. Contractions really begin when the baby's head pushes against the cervix, and there are nerves in that tissue that detect that pressure. And so the nerves then feed back up to the brain, causing it to release a hormone called oxytocin. And oxytocin directly causes the uterus, which is a big giant muscle where the baby is, living inside, causes the uterine muscle to contract. So oxytocin is released, the uterus contracts, and of course when the uterus contracts up here, it contracts at this top portion, it pushes the baby down again further, putting pressure on the cervix. And so then again, that pressure is detected, sent to the brain, more oxytocin is released, uterine contraction again, baby's head pushes further on the cervix, repeat, repeat, repeat. And so you see that the positive loop is perpetuating that stimulus, perpetuating the baby's head on the cervix. Now, all positive loops will eventually end. And in this case, for example, once the baby is born and out of the body, then you don't have that stimulus, the head of the baby, facilitating this positive loop. So positive loops will eventually end, but not until the stimulus is ultimately removed. If you were to graph a positive loop, it could look something like this. It could start at a set point and continue to increase, 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 increase. Now, I know that this is a market share representation, but really, positive and negative loops extend outside of the world of anatomy. So this is entirely appropriate. This is positive feedback where we are moving away, 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 away from the set point, increasing, 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 increasing. Or we could have seen the opposite trend where we decline, 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 decline away from that sort of initial starting point. Okay, so let's talk about an example. Here is an example of a practice question. Now, I know the video covered it, but after eating a meal, your blood glucose levels increase. Islet cells in your pancreas detect the rise in blood sugar and release insulin into the bloodstream. Insulin binds to receptors on cells throughout the body, allowing the cells to take up glucose from the blood. This lowers blood glucose levels back to normal. So, given this scenario, and the reason that I'm including it on the slide and we're practicing it here together is because your kind of exit slip to finish out today's lesson is to do a practice question like this on your own on a Google form. So let me show you kind of what we're looking at and the key components that need to be identified. So you read the scenario. We've got blood sugar, blood glucose levels, insulin, etc. And then you need to be able to identify A through E within the scenario. So first of all, what type of loop is it? Well, let's think about this, and I want you to kind of get this in your head so you have the opportunity to practice. If you're looking at this scenario, you eat, blood glucose rises, that triggers your pancreas to release insulin. Insulin will remove glucose from the blood, lowering it back down. What type of loop does that sound like? Think for a second. Get an answer in your head. It is a negative feedback loop. If you said that, you are correct. You also need to be able to identify the stimulus. So, what is the thing that is detected? What is the stimulus here in this problem? The stimulus is sugar in the blood, your blood glucose levels. You need to be able to determine the receptor. So, what is detecting the stimulus? So, think about that for a second. What is detecting the now identified blood sugar? Islet cells in your pancreas. Now, that's a little bit weird. We talked about in the notes that it should be typically a sensory neuron, but the pancreas is weird. It sort of functions as a gland, as a organ, and as even a part of like the nervous system in detecting. So the receptor or the effector here is your pancreas. The control center, kind of weird. The control center most of the time is our brain and our spinal cord. But in this example, the pancreas, because it needs to respond so quickly, the pancreas acts as its own control center. And then last, you need to be able to identify the response or the effector. What is the response here? We see the release of insulin, and insulin will lower blood glucose levels. Okay, so those 5 things pulled out of a practice scenario is what you are getting ready to do to end your lesson for today. So you should have taken the notes for this video. When you're done, you can go back to the daily plan and click on the exit slip, which is a Google form that gives you another scenario where you identify these 4 components.